All right, number 8. So if you have cube root of z times the 5th root of z squared. So how do we deal with that? Well, good news is the bases match. Because the bases match, we're going to be able to do something. And it doesn't look like initially that we can do anything, but if we start to apply all this different stuff that we're doing with taking a radical and writing it as a rational exponent, this becomes z to the 1/3 times z to the 2/5. And now it starts to have a little bit of a better feel where if the bases match, properties of exponents is we can add these exponents together. But we can't add them together as is because the denominators don't match. So now you got to dive back into the world of fractions and find yourself a common denominator. So between 3 and 5, they both can become 15. So to make that happen, we're going to multiply this by 5, multiply this by 5. Whatever you do to the bottom of a fraction, you have to do the same thing to the top. And essentially you're multiplying the whole fraction by 1, so you're just changing the look of it. So that becomes 5/15 times z to the other exponent. So this one we're going to multiply top and bottom by 3. So that becomes 6/15. And now, with a little bit of manipulation, now we're able to add the exponents together. But because we had fractions, we have to do that extra step of finding common denominators. So now we have z, denominator is 15, and we're able to add these numerators together. So that becomes 11. All right, so we have a couple more to do. So number 9. If we have the cube root of x being distributed into the square root of x minus the cube root of x squared. Now these are not able to go together. In order for you to add or subtract radicals, they both have to be either square roots or they both would have had to have been cube roots. And since the radicals don't match, they're not considered like terms as far as adding and subtracting goes. But as far as multiplying, because they all have the same base, we're going to be able to do something with it. So, again, one of the better methods is let's rewrite everything so they're not radicals. So this will be x to the 1/3 distributed into x to the 1/2 minus x to the 2/3. So really you have almost exactly the same problem that you did on the last one. So the last one is we're multiplying pieces together. And when we multiply pieces together that have the same base, you're adding the exponents. So you have the exact same look, it's just a little bit more of a complicated version of it, but you're multiplying those two pieces together. So a couple things you can do with this is, in general, you're multiplying x to the 1/3 times x to the 1/2 minus x to the 1/3 times x to the 2/3, because you're going to be distributing this in. All right, so that's really the math that's happening. So there's your x to the 1/3 that's distributed into those two pieces. So you could set it up like this, and then now you have to add your exponents together. Or at the very beginning, before you kind of distribute this, is we're going to have to add these exponents together because that's the property. So we're going to do the same thing that we had to do with the previous problem, was find common denominators. And I might as well find common denominators for everything. So, or you can end up doing it here anyways. And if you notice, they may end up having the same kinds of a look to them. So either way is going to work, and we'll finish this one as well. So here you can just say, all right, well, they can all be, let's see, 6. So if they're all going to be 6, you're going to multiply this by 2 times 2. So that's going to be x to the 2/6 times, here you're going to multiply by 3, multiply by 3. So that's going to be x to the 3/6 minus, and here you're going to multiply by 2. So x to the 4/6. All right, now you can multiply those together, you can multiply those together. So if you multiply those two together, you're going to add those exponents together. So that's x to the 5/6 minus 2/6 plus 4/6 is going to be 6/6. And this we can reduce. We cannot reduce that. So it's x to the 5/6 minus x to the 1st, which we don't need. All right, so that's one way to do it. Or, since you don't need to get a common denominator with everything, it might be nicer just to kind of multiply it like this and individually figure out what your common denominator is. So here, you still got to multiply this by 2 and this by 3. So we'll multiply top and bottom by what we need to make a common denominator. So that's going to be x to the 2/6 times x to the 3/6. Now, however, a little bit less work than what we did over here is you already have common denominators, so you can just add them as is. So that's just going to be x to the 3/3. So common denominators, we'll add their numerators together. Denominator won't change. So here we'll add our fractions together. X to the 5/6 minus x to the 1st. So most likely it's probably going to be a little bit nicer to not worry about finding an overall common denominator because they may have nothing to do with each other. So distribute this in and then kind of set it up though, and then you can worry about finding your common denominators if you need to. All right, one more. So in the last problem, we're going to have the 5th root of 32y squared divided by the cube root of 8y to the 4th. So on this one, it looks as if we're not going to be able to do anything, all right? Because you can't divide a 5th root and a 3rd root. However, because of all of this and finding common denominators and all that sort of stuff, it's much easier if we just kind of rewrite it. So one of the first things we're going to do, though, is let's just look at the individual pieces. So since we have numbers mixed with variables, I might be able to do something with the 5th root of 32, but I probably won't be able to do anything with the 5th root of y squared. That's okay. We'll write it as a rational exponent. And then same exact idea on the bottom, cube root of 8 times the cube root of y to the 4th. All right, so good news. We can do the 5th root of 32. That's 2. We're going to rewrite this as y to the 2/5 power. We can cube root the 8, which is also 2, and y to the 4/3 power. All right, now we can start to mess with things. First off, the 2's are going to cancel each other away, and they're going to become 1's. And we have the same base. So since we have the same base, we're going to be able to add or subtract our exponents. Since it's division, we're going to be able to subtract our exponents. So let's rewrite that. We have a 5 and we have a 3, so we need a common denominator of 15. So we're going to multiply top and bottom here by 5. We'll multiply top and bottom here by 3. So that'll get us a y to the 6/15 over a y to the 20/15. So how do we deal with that? Well, we have same base. Technically the property is we're going to subtract them, but I look at it a little different. I look at where I have more y's. I have 6/15 on the top. I have 20/15 on the bottom, so I clearly have more y's on the bottom. So these are going to cancel a chunk of these, but not all of them. So I have 14/15 more on the bottom. And you can't have nothing on the top to Technically, there's ones attached to these, and that's what it will reduce down to. If you did the subtraction and you did 6/15 minus 20/15, you get a y to the negative 14/15, which would then bring it down anyways because of the negative exponent. All right. And that is writing radical expressions as rational exponents.